Okay, so welcome back. In today's lecture, we're going to discuss how the derivative of a function can be used to iteratively find the minimum of a function. And along with this, we'll show how this has applications in machine learning. So the general problem at hand for today's lecture is the following. We want to minimize some function x over some variable x. And x in our case is just going to be a real number. Okay? So, with that being said, we'll start with a very simple example problem where we know the actual solution. So, suppose we want to minimize f of x equals to, I don't know, x minus 2 all squared plus 1. Okay, so this is a very simple parabola function that's been shifted to the right by 2 and then raised up by 1. So what does it look like? So it more or less looks like, so over by 2 and then up by 1. The vertex of that function is right there. And then when x is equal to 0, it'd be 4, so it's like 5 up, so 1. It'll be up there somewhere. I'm just going to leave the tick marks off because it'll be hard to draw it in a way that'll be useful for us. But it basically looks like this. So clearly here with this parabola, right? This is again, this is f of x equal to this function. So this has a minimum right there. So just, we know the answer, okay? We know the answer. So f of x is minimized at x equals to 2, right? That's right here. That point right there is 2 comma 5 or 2 comma 1, right? So we know that's the minimum. We can just like easily observe that, right? So what we're going to do is that we're going to suppose that we don't know the minimum, right? This is a very simple function. But let's suppose that we do not know this answer. Can we still find it? Well, we need to observe a few things. Okay, so supposing we don't know it, we do not know this. We do know a few things. Okay? And what are the things that we know? What is the value? So like this is like x equals to, I don't know, call it c. Right? C is actually 2, but we don't know that. We're pretending we don't know that. So what is the value of the derivative? Well, actually, we like this function, suppose we know the derivative. So like f prime of x, if you've been on top of the homework, you'll know that this is 2 times x minus 2. Like we know the derivative. Okay, we can like somehow evaluate it. What is f prime of c? What's the value of the derivative at x equals to c? Anybody? What was like the most important thing that I emphasized about the derivative? What does it tell you? The slope of the what?
Tangent line?
Right, the slope of the tangent line to the curve at that point. What is the slope of the tangent line to the curve at this point? What is the slope of that line?
0.
0. It's 0. It's just a flat line. There is no slope. We know that because with the videos that I posted yesterday, that minimum occur at critical points, right? This is like a consequence of this being a critical value. So we know that minimums occur at critical numbers. And if you have watched those videos, recall that critical numbers are values where the derivative is either 0 or does not exist. Okay? So what else do we know? Okay, coming back over here.
My screen is kind of blurry. I don't know if it's just mine or.
How about now?
Still blurry.
Well, let me pause the recording real fast. All right, so we're back. And again, this recording will be posted on YouTube, so it'll be clear there. But I'll speak everything out. So part 4, so just to recap, we know the derivative of the function. We know that minimums occur at critical numbers, which means that the value c that we're trying to minimize the function with, we know the derivative evaluated at that c is going to be equal to 0. So how could we find this minimum? Well, in part 4, maybe I'll write real big here. I'll start over here. So if we are at x equals to like, I don't know, maybe not x, but like say like x1, then there's a few things that we can observe. Okay, what is the first thing? Well, if the derivative of the function at x1 is greater than 0, so like we're on like the curve somewhere, and here's like x1, and then here is the tangent line right there. So this line here has slope equal to f prime of x1. If it's greater than 0, right? If that derivative is greater than 0, meaning it has positive slope, what does this mean? It implies that if we go to the right, we're going to go up the curve. If we go to the left, we're going to go down the curve. So this means we need to decrease x1. And if we look at the slope of the tangent line at this point here, we're trying to find the minimum value, right? Or a minimum, a local minimum. If it's positive, if we increase x1, we're going up the curve. If we decrease, we're going to go down the curve. And our goal is to find that minimum value. Okay. Okay. What about f prime at x1? But if that's less than 0, then we need to increase x1. Right, we need to add to it. And why is that? So suppose, again, I'm trying to draw everything really big right now to help with the blurriness. So like, if we're like here, and the slope of the tangent line is like this at the curve, right? If it's negative, that means if we move this way, we're going to go down the slope. So we need to go this way to try to find a new guess that's closer to here. So the derivative is telling us which direction to move. The derivative is positive, we need to move to the left to find a smaller function evaluation. If the derivative gives us a negative value, then that means we need to increase our x to find a smaller evaluation of f. So with this notion, we can kind of like take little steps, right? We can make a guess and then use the derivative to tell us to take a walk either left or right, and we can try to isolate that minimum point by just iterating this over and over. So the idea behind this is the following. It's called gradient descent. Make an initial guess. Call it x1. Initial guess. And then for every, you make a bunch of new guesses. x7 plus 1 is equal to your old guess minus a number called alpha times the derivative at your old guess. And this right here is alpha. That's called the learning rate. Or step size. It's just a number between 0 and 1. Well, right here. 0 less than alpha, less than or equal to 1. It kind of scales the steepness of the slope of the tangent line. So, with that being said, let me pull up a Jupyter notebook and let's see if we can find that true minimum value for that function. So I'm going to pause the recording again. Okay, so here we are. I've navigated to our course folder that I made for this course, and I'm going to open up a new Julia Jupyter notebook. Okay, so you're going to see me write some code maybe that you haven't seen before, but I'll kind of walk through. In this notebook, we're going to solve the optimization problem that we were just talking about. And we want to visualize this along the way. So in order to visualize things, we're going to need the plots package. So using plots. And then in this same cell, I'm going to go ahead and define my function, f of x equals to, what was it? X minus 2 all squared plus 1, like that. And then I can take a look at the plot real fast just to verify what it looks like. So plot F. And then maybe give it like a label. F of x equals to x minus 2 all squared plus 1. And maybe that'll work. So then I'll press Shift Enter or Shift Return. It's taking a second to load the functions from plots.jl. That's why it will take a little bit longer than the other functions. And we can see our function here. Maybe I'll restrict my x limits to be like -2 to 6 or something. So I can just come back up here in my plot function, move that down. You don't have to stack them like this, but I just find it easier to read when they're stacked. So x lims equals -2 to 6, then be sure to put a comma. So function, comma, keyword argument, comma, keyword argument. All right, so there's our function. And I don't see the, I would like to see the y-axis, like the y0. I see like 3, 0. So I'm gonna set my y limbs to be different. And I'm just gonna copy this code and use it over again later. So y limbs, say maybe like -2 to 12. Let's see what happens there. Shift Enter. All right, so here we can clearly see, here's the origin, 0, 0. Here is the minimum value here. And we're going to implement gradient descent to solve this. Now, just in case you weren't able to see what gradient descent is, I'm going to stick in a little markdown cell here with gradient descent in it. So markdown, I'm just going to make it look nice. You don't have to know how to do this. I'm just making it for teaching purposes. Gradient descent, and then so how does this work? 1 x1 math type initial guess. Let's see if that looks right. And then part 2 iteratively find new guesses maybe with, and then I'm going to put some more math type in here. X of n plus 1 equals to x of n minus alpha. This is called math type. You don't need to know how to do this. I'm just doing it because it's going to look nice and we can reference it back. X of n. Right. And then I can add like a comma here where 0 strictly less than alpha, which is less than or equal to 1. Okay, so this is gradient descent. So what we're going to do is we're going to make an initial guess, and we're going to see if this our new guesses are going to get closer or farther away from where we know the answer to be. Okay, so let's make a guess. Let's call it like x1. Maybe we'll guess like 4, right? So our guess is 4, and okay, so 4.0. Okay, so now we can even plot where our guess is at. Okay, so I'm gonna grab that code up there, come back down there. So that plots the function, and then on top of that, I'm gonna scatter a point. Scatter. And I'm gonna do in brackets x1, comma, in brackets f of x1. So to scatter points, you need an x value, which is that, and then this is a y value. And f applied to that x is going to give us a y value. And then I'll give it a label. X1 comma f of x1. And the exclamation point is plotting on top of this plot here. Okay, so there's our initial guess. X1 gives us this value. Actually, I can do this all over again. I can say like y1 is equal to f evaluated x1. So we can like keep track of our y's. So how high up is y1? It's 5.0. Okay. So let's see if gradient descent is doing anything. We have to choose an alpha. So we can say alpha equals to, I don't know, some number between 0 and 1. Let's say like 0.75. And then we can say, well, what's the rule? So in this case, so we start with 1. So this will be x2 is equal to x1 minus alpha times the derivative at x1. Oh, so we need the derivative as well. So I'll call this function df of x. And we know what the derivative of this is, of this function. It's 2 times x minus 2. 2 times x minus 2. So that's the derivative. And then we can say, okay, x2 is equal to x1 minus alpha times the derivative at x1. And then we can say y2 is equal to f applied to x2. All right, so this right here is literally, see how there's a 2 there, there's a 1 there, there's a 1 there, that's the derivative, this is the learning rate. It matches up exactly. x2 is equal to x1 minus learning rate times the derivative at x1. Right? So then what we can do is kind of just grab this code here, this plotting code, and then we can plot. So this plots the function, this plots our first point. I can copy this and then paste, and then just do it with x2. Change all those x1s to x2. So do you see what happened here? So our initial guess was 4. What's our new guess? X2. It's 1. So we moved all the way over here to 1. But here's our guess. We subtracted alpha times the derivative. So the derivative is positive. So subtracting a positive number, we're going to move this way. And this is our new point. Okay. So then let's just do this all over again. So I can literally just copy this code here. Come down here. And then just instead of x2, x3. And that is instead of x1, x2. So this is gradient descent again. And then just copy this code here, come down here and replace the 2's by 3's. Now we're right there. So do you see how we took a step this way, but then the derivative was negative here, right? So so it's like, this was our second guess, or no, sorry. So second guess is right here. And then we subtract off alpha times the derivative at x2. And what do we get? 2.5. So we subtracted and we moved over here. Right, because minus a negative value is going to shift us this way. And then you can kind of guess what's going to happen next. So just copy that. Now I'm going to make an X4. So replace the 3s by 4s and the 2s by 3s. And then plot the next point. 4, 4, 4, 4. Now we're right there. So what do our guesses look like? So let's just look at it. So there is a thing in Juliet called a macro, and it's basically a function. And there's a really nifty one called show. So if you just want to show the variable, you just do that. Like if I just run this, that's what x1 is equal to. So if I just take that at show thing and I copy it a bunch of times, so that x1, x2, x3, x4, and then I don't want the value to appear at the very end, but it's fine. So look what's happening. Our first guess was 4, and then we moved to 1, and then we moved to 2.5, and then we moved to 1.75. Right? So where are we going? I guess I'll do this one more time manually. This is not how you would program it generally. This is just like an educational thing. Let's do x5 now. x5, x4, x4, 5, x5. And then let's plot those points. 5, x5, 5, x5. Press shift return. Now we're right there, right? And again, if we just like look at where these values are going, .125. So, okay, are we getting closer? Yes, we're constantly moving back and forth, back and forth. So to make this a little bit more, like I'm gonna put all this code in one cell so we can play around with something. Let's say, what do I wanna do? Okay. No, I don't want that. I'm going to start all over again. So I'm going to copy that, paste. So what do I want? 4. Actually, this is like not efficient to do it that way. I'm going to come back up here. I'm going to grab these, copy that, put it here. I'm just going back up and I'm getting everything to run in one cell. Copy that. Come back down here. And then I already got that one, maybe this one. Copy that one. Right there. And then we took a guess that x1 was equal to 4.0, and we said that alpha was equal to 0.75. So we should get the exact same plot. Everything is the same, it's just everything's running in one go. And we do, right? So, and then if I run this, we can see that we're getting closer to 2. But what happens if I change my alpha? What if my alpha is like 1? What happens if I make a learning rate of 1? What's going to happen to the points? Oh, we just oscillate between 4 and 0, 4 and 0, 4 and 0. So if your learning rate is too big, you might always like take too big of steps, right? We started at 4, we jumped to 0, but then we jump back to 4, we jump back to 0. So maybe that's not an optimal learning rate. What about if we take a learning rate of like a small one, like 0.01? Oh, the learning rate is too small. We started at 4, but then we only took a little step to the left, little step to the left, little step to the left, right? That was with learning rate 0.01. And you can see if we look at our values of x, they're going down. It's going really, really slow. You would imagine like it'd probably be like 1,000 iterations before you'd be anywhere near the actual value. So what about something like 0.25? Looks better. It's kind of slowly getting down there, and that looks all right. But how do we know, like, how do we know that we're getting closer to the, because like we won't have this graph, right? How would we know that we're getting closer? Well, what if we look at the derivatives value at each of our guesses? What do we know that's going to happen when we get to like when we get to a minimum? We know the derivative is going to be equal to 0, right? So one way that we can check if we're close, right? If we don't have like a visualization here, is that if each iteration is getting closer and closer to 0. So what I'm going to do now is I'm going to show you how this can work for like it with a looping type of process. So x, so guesses equals to, let's say, x1. So we'll put like x1 in here. I'll just call this capital X actually. All right, so x1 equal to 4.0, and just put x1 into this array. And then we can say something like while, by the way, just so you know things about Julia syntax, x is a vector, and we can access the last vector and last entry of that vector by typing end. So like if x had like things like this in it, right, then I can access the last one by doing end. So that'll come in useful with the following loop that I'm going to do. So a loop, as you'll see, I'll provide a YouTube video for you guys to kind of learn more about loops after lecture. So while the absolute value of the derivative applied to the last guess that we made, so while that is greater than 0.1 or something, I also need to put in like a counter thing. So, and I'll explain why in a second. And I less than like 1,000. Like I don't want this while loop to run forever and avoid it. Oh, not and, sorry. Double ampersand is the logical and. So for this to enter into this code block here, this has to be true. So the derivative at our last guess needs to be bigger than some small number. And then also while this counter is less than 1,000, what are we going to do? We're going to say x new is equal to x end minus alpha times df applied to the last guess that we made. Okay, and then once I do that, I'm going to push this new guess that we made into x. So there's a function called push in Julia. And what this is going to do, so like when this makes the first one, it's going to take this value, apply gradient descent to it, and then it's going to take that and put it like right at the end behind this one. So that'll be our last guess. And it's going to keep on doing this while the derivative is big or while I is less than 1,000. So I need to increment I. So this syntax here is just incrementing I by 1. Okay, end. And let's see what happens. It's done. So what does X look like? 4, 1, 2.5, 1.75. That's basically 2 right there. And the reason for that is that if we apply the derivative to the last one, which is 2.3125, it's 0.06, which means it violated this part right here. That's smaller, so this was less than this, so they'd break out of the while loop, and that was the last guess that we made. I could make it better, right? I could make this like a smaller number like that, 0.01, and then look at X. And then if I look at the end, it's like a small value. And then I do absolute value because it could be negative. But now, like, that's a very small number. This was our last guess here, which is essentially 2. It's basically 2. In fact, we can plot that as follows. Copy that. Do that. And then y is equal to f applied to the whole array x. And we use this like dot notation to take f and apply it to everything in there. And then I can scatter those points. X comma y. There. They all start jumbling in. And okay, so I think this concludes my short introduction to gradient descent. So I'm going to go ahead and stop this recording here, and we might pick back up another one.